now we're going to get into atomic theory. Now, since John Dalton was the first person to actually put together a theory, a model of what the atom really is, that's one of the things that he's the most famous for. Like, yes, he established quantitatively some of the fundamental laws that are still in use today. Another thing that he did was the first atomic theory. Now, if you remember from Chem, not every one of his postulates are exactly correct. They're not 100% spot on. But that's not the be-all, end-all. The fact that he put together a model was actually one of the foundations that allowed this study to spring forward, right? Because he gave the rest of the scientific community something to test, something to work on. Now, so yeah, here we go. And again, this is all based on knowledge of the time, right? And so that'll be a little bit more important. I'll explain why this is important a little bit later. So there are 4 postulates of Dalton's atomic theory of matter. Now, if you remember from my Chem class, I'm like, well, wait, our book said that there was 5. Yes, that's because they were broken up into 5, right? Every single statement that is made in these 4 is present in those 5 postulates. It's just that our Gen Chem textbook wants to break it into 5. I hope that doesn't throw you guys off. But every single idea that was in those 5 is in these 4. Okay. I actually believe it's number 4 that was actually broken up into an extra separate one. That atoms are neither created nor destroyed in the course of ordinary chemical reactions. I believe our Gen Chem book takes this one and then makes it a number 5. So I hope that doesn't throw you guys off. Anywho, number 1, all matter is made of atoms, this fundamental chemical particle, and these atoms, atomos, they are indivisible, because that's what the word atom actually means, and indestructible objects, and they are the ultimate chemical particles. Second postulate, all the atoms of a given element are identical in both weight and chemical properties. However, atoms of different elements, right, so like oxygen versus nitrogen, have different weights and therefore different chemical properties. Number 3, compounds are formed by the combination of different atoms in a ratio of small whole numbers. And then lastly, a chemical reaction involves only the combination, separation, and rearrangement of atoms. Why? Because they're indestructible, right? Indivisible, indestructible. So atoms are neither created nor destroyed in the course of ordinary chemical reactions. Now, we know that these aren't entirely true, right? Since then, the subatomic particle has been discovered, right? In fact, atoms are divisible. And so it leads us to the understanding that the word atom, as it's applied now, is actually a misnomer, because they can be divided. They can be divided up into, right, protons, neutrons, and electrons, right? We know that now. They didn't know that then. They had no way to know that then. Let's see, and isotopes were discovered, right? So we're going to have to put a little bit of an asterisk on number 1 because they are divisible. And you know what? I'm not going to put an asterisk on indestructible. And I'm not going to put an asterisk on atoms are neither created nor destroyed because he stated in ordinary chemical reactions. And so he went to say, oh yeah, but we can have a nuclear reaction and we can split that atom. Well, that's not an ordinary chemical reaction. That's actually a really, really big deal. So we can't call that an ordinary chemical reaction. But number 2, we'll have to put an asterisk on number 2 because, right, it says that all the atoms of a given element are identical in both weight and chemical properties. But later on, isotopes were discovered, right? Isotopes were discovered. Now, if you remember what an isotope is, we have 2 of the classic examples are carbon-12 and carbon-14. Right? So in terms of carbon-12, right, it's carbon, so it's definitely going to have 6 protons. Well, so is carbon-14 because it is carbon. It has to have 6 protons, or else it's not carbon.
The big difference here is the number of neutrons, right? This is carbon 12, right? And so in order to get to 12, I need 6 more subatomic particles, so 6 neutrons. With carbon 14, I would need 8 neutrons. And so this weight, this difference in weight, the atomic weight, breaks this second postulate, right? Now, it's not like, oh, boo on John Dalton. He had no way to know this. It was absolutely impossible for him at the time to understand that, essentially because of inadequacies in instrumentation. Now, here's where we really take the next step, right? Take the next step. 1809, Joseph Gay-Lussac, and this is actually this is not like he got married and instead of the wife agreeing to take his last name, they just hyphenated, because that actually happens in our culture today. This is actually fairly common in the old aristocratic system of naming. That's just a normal last name for back in the day. So that's just his last name, Gay-Lussac. He performed experiments at constant temperature and constant pressure. Remember how in empirical science it's really, really important to control all variables. Otherwise, you run the risk of being considered pseudoscience. So at constant temperature and pressure, the measured volume. So he's controlling temperature, check. He's controlling pressure, check. And he's studying the volumes of gases as they reacted to each other. And I'll write this how we would write it today, right? For 2 volumes of hydrogen, so it's H2, combining with 1 volume of oxygen, we will react to form 2 volumes of water vapor. Remember that term water vapor is dedicated as a descriptor for substances that are in fact in the gas form, but typically, normally, at room temperature, they're a liquid or maybe even a solid. Right? That's why we use the word vapor here. And before we go any further, let me remind you about the diatomics. Right? Diatomics. This is actually some of the studying. This is some of the data that went into identifying the gens as diatomic. And so there are 2 rules that are really, really helpful, or should I say mnemonics that are really, really helpful. There's Brinkelhoff. Right, so bromine, iodine, nitrogen. That's not exactly how you spell it, so it's H-L-O-R-I-N-E. Hydrogen is actually harder to write in a line than I thought it would be. Oxygen, and then fluorine. Right, so there's this mnemonic, Brinkelhoff. All these 7, 1, 2, 3, 4, 5, 6, 7. These elements are always going to be diatomic, so it's going to be R2, I2, N2, Cl2, H2, O2, F2. Brinkelhoff. Or you can think of the gens. All of the gens are diatomic. So that would be nitrogen, hydrogen, oxygen. But you think, well, okay, that works for nitrogen, oxygen, and hydrogen, but what about bromine, iodine, chlorine, and then fluorine? What about those? Right? Those don't end in gen. Well, guess what? Those are all halogens, right? In group 17 over there on the far right side of the periodic table, that they're all in the same group. Bromine, iodine, chlorine, and fluorine are all in the same group. They're the halogens, right? So these diatomics, nitrogen, oxygen, hydrogen, and all the halogens, right? So those are diatomic. Anywho, another experiment that was done over and over and over. We get 1 volume of hydrogen with 1 volume of chlorine, which is a halogen, to form 2 volumes of HCl. And this study right here was one of the things that actually led scientists to conclude that there were such a thing as diatomic molecules. In 1811, Amadeus Avogadro, who's an Italian, proposed his hypothesis regarding Gay-Lussac's work. In fact, he actually admitted that he was just piggybacking off of Gay-Lussac's work. It's true. But because of that and then some other things, he was basically ignored for 50 years, right? So essentially 50 years of nothing was accomplished, because this actually is foundational to understanding the quantitative aspect of the experiments that would follow. And one of the biggest things that we can take away from Avogadro's studies, right? You thought he was just famous for that number. We're going to use that number, by the way, so please remember that number, the 6.022 times 10 to the 23rd. But Avogadro's hypothesis, right, which is pretty famous, right? Notice it's in a gray box. So was Dalton's atomic theory, the 4 postulates there, so it's a pretty big deal. So at the same temperature and pressure, so we're controlling for temperature, we're controlling for pressure. At the same temperature and pressure, equal volumes, so the same volume of different gases contain the same number of particles, right? So let's check out this visual representation of these two equations that we just looked at right here. But now we're going to pay attention to the volume, so the size of the box. Notice that any box that has 2 molecules in it is the same size, has the same volume. Right? Now, we, understanding what an atom is in the way we do today, it's easy for us to say, oh yeah, each one of these molecules takes up the same amount of space, the same volume. And so if they have the same number of molecules, they have the same number, they'll have the same space, they'll have the same volume. But that's not what Avogadro was working with. He went the other way because he was not able to count how many molecules were in the volume. He knew what the volume was. And from knowing that there was the same volume, right? That's why we have here equal volumes. He started with equal volumes, and then he concluded that they did have equal volumes because they had the same number of particles. And you see that this larger box. There are 3 examples of larger boxes here. They're all the same size box. They all have 2 molecules in them. There are 3 examples of the smaller box, which is more of a cube. Only has 1 molecule in each of them. All right, so that's Avogadro's hypothesis.